What about subtraction mod n? If a is greater than b, then a minus b mod n is exactly what we'd expect. And if a is congruent to r1 and b is congruent to r2, then a minus b is congruent to r1 minus r2. Or is it? Let's try an example. We could find 35 minus 18 and reduce mod 11. So 35 minus 18 is 17, which we can reduce to 6 mod 11. But we also have 35 congruent to 2 and 18 congruent to 7. And this suggests that 35 minus 18 is congruent to 2 minus 7, which is negative 5. So what should we make of negative 5 mod 11? So a useful intuition. The modulus is the least positive number that acts like 0. And so we note that 11 is congruent to 0 mod 11. And so if I add 11, it's like adding 0. So negative 5 plus 11 is congruent to negative 5 plus 0. And so that tells us that 6 is congruent to negative 5 mod 11. The fact that a negative number is also equivalent to some non-negative number mod n means that we can work with signed numbers in exactly the same way we work with unsigned numbers. In fact, we can do even better. Since a minus b is the same as a plus negative b, this means that subtraction mod n can also be performed as addition mod n. For example, let's try to reduce the numbers. Since 13 is congruent to 0, we can add 13 to any number, and so negative 5 plus 13 is the same as negative 5, and so we get 8 congruent to negative 5 mod 13. Let's try to multiply. So we note that 15 is congruent to 4 mod 11, so we could compute the signed product in the ordinary way. Since we're working mod 11, adding 11 is like adding 0, and in fact we can add a multiple of 11, which is like adding a multiple of 0. So negative 32 plus 3 11s is congruent to negative 32 plus 3 zeros, and so we get 1 is congruent to negative 32. Alternatively, we might note that negative 8 is congruent to 3 mod 11. So we could have reduced both factors at the start to get What about division? Remember, never divide. But we should avoid it. Could we still define division for arithmetic mod n? Well, let's see what happens. A useful guide here is always ask how. When we divide integers a divided by b, we can repeatedly subtract b until we get a remainder between 0 and b. We stop at this point because if we subtract b again, we'd get a negative number. But if we're working mod n, any negative number can be replaced with a non-negative number. And this means the only natural stopping point is when we reach 0. Let's try to find 34 divided by 15 mod 11. First, we note that 15 is congruent to 4 mod 11, so subtracting 15 will be the same as subtracting 4. So how many times can we subtract 4? So 34 is congruent to 1 mod 11, and so 34 minus 15 is congruent to 1 minus 4. That's negative 3, but mod 11, that negative 3 becomes 8. And now I can subtract 4, and again. Since we can subtract 4 3 times, this suggests 34 divided by 15 is congruent to 3 mod 11. However, there is one thing we have to worry about. Because we can represent numbers in several different ways, it's conceivable we might get different answers. So what if we subtracted directly? 34 minus 15 is 19. Minus 15 again is 4. Minus 15 again is negative 11, which is congruent to 0 mod 11. And again, we can subtract 3 times, which again suggests the quotient might be 3. What if we used 1 mod 11? So we subtract. That gets us negative 14, which is 8 mod 11. We'll subtract again, which gives us 4 mod 11. And if we subtract again, we get 0 mod 11. And this again suggests that the quotient is 3. Let's think about this a little bit more. If 34 divided by 15 is congruent to 3 mod 11, this suggests that 34 is congruent to 3 times 15. And we can expand the right-hand side, 34 congruent to 45, which is, in fact, true. And all of these suggest we might be able to define division mod n. But we'll need a better algorithm for computing a divided by b. So let's take a look at that next.